institute here. I cannot tell you how great it is to be in front of actual people for once. This was going to be my first Blackboard talk since the beginning of the pandemic, but due to circumstances, it's going to be my second slides talk ever. So let's see how it goes. So I will be reporting on a joint work with A.Padrol, Y.Palu and V.Pilaud. It's a work from 2 years ago now. Since the title of the workshop is New Developments in Representation Theory Arising from Cluster Algebras, I will not really be talking about applications to cluster algebras. Rather, I will start with the motivation from cluster algebra and then talk about the representation theory tools that we had to work with in order to then do these applications. But I'll spend more time on the representation theory. Okay, so let's start with cluster algebras. So that's the context for this talk, even though I won't be really working with them. So if you have a cluster algebra here, as defined by Fomin and Zelevinsky, a cluster algebra is a commutative algebra that sits in an algebra of Laurent polynomials. And I want to talk about categorification. So on the other side of this picture, there's a triangulated category, or maybe an exact category, or maybe it depends what you prefer. But in this talk, it's going to be, for the moment, the triangulated category, the cluster category as defined by Calderon-Shackleton-Schiflot and Juan Marshall-Ferret and Todorov, and then Claire Amiot, the generalized cluster category for an equivalent potential. And this is a triangulated category whose objects, or maybe certain objects, correspond to generators of the cluster algebra. So the way to do this is to define a cluster character or Calderon-Shackleton map that takes an object in the cluster category and spits out a Laurent polynomial in general. But if you start with good objects like reachable rigid objects, these Laurent polynomial happen to be cluster variables. So this is the motivation for what I'm going to talk about, even though this picture will not really occur during my talk again. And this picture is good because it's a good categorification of a lot of the information in the cluster algebra. So categorify cluster variables. So indecomposable, reachable, rigid objects are sent to cluster variables. Categorify clusters. So reachable cluster tilting objects are sent to clusters. It categorifies mutation. Mutation corresponds to certain pairs of triangles called exchange triangles in the cluster category. And finally, it categorifies G vectors, F polynomials. There's a lot of information that you can find in the cluster category. And today, I want to focus on the last one. I want to first show you why the cluster category with its triangulated structure is a good categorification of G vectors, then try to convince you that it's not the best categorification of G vectors and see how we can improve on this. If you start with good object. This is the aim of my talk. Now that was the motivation. Now what's the context? I will start with K, a field, not necessarily algebraically closed. This will allow us to treat non-simply laced Dynkin types. And then C, that's a long sentence. C is going to be a K-linear category. It's going to be, let's use the same order, Hom finite. So the Hom spaces are finite dimensional. It's going to be called Schmidt. So in particular, you have a nice unique decomposition of each object into a direct sum of indecomposables. It's going to be 2 Calabi-Yau. If you know what it is, you know that this is a nice homological duality inside of that category. If you don't, I'm not going to use it really, except behind the scenes. It's a triangulated category, and I will denote the suspension factor by the capital letter sigma. Now, inside this category, I will assume that there's a nice object, a basic cluster tilting object. So it's an object that generates the category. It's rigid, so that's the first. Can I use this with my left hand? Yeah, okay. This is the first condition here. It has no self-extensions, and it's maximal for this property in a certain sense. So if it has no extension with another object, and this object was a direct sum of direct summons of T. I will also assume throughout that I have a good decomposition of T into indecomposable objects. So T1 up to Tn are the indecomposable summons in a decomposition of T. They're all non-isomorphic, pairwise non-isomorphic. So that's the categorical context. I have a triangulated category to Calabi-Yau with a cluster tilting object. The main example I have in mind is cluster categories or generalized cluster categories, but everything I say works in this apparently more general setting. Okay, now I want to talk about categorifying G vectors, so let's say what this means. So I recall some notation above here, and the main result that helps us categorify G vectors is the following, due to Dehy and Keller, and also to Palu. If you have such a category as before, any object X sits in a nice triangle like this, where the first two terms are direct sums of direct summands of T. A way to phrase this would be that any object is presented by add T. If you're used to representation theory, you can think of these people in add T as projective modules and saying that any object has a quote unquote finitely generated presentation by these projectives. Yes, finite presentation. Okay, so this is a consequence of the axioms. So the index or the G vector of the object X will be defined as follows. You take this object here, you view it in the Grothendieck group, the split Grothendieck group of add T. That's just the free abelian group generated by symbols that correspond to the indecomposable summand of T. And the index of X, or the G vector of X, is the class of T0 minus that of T1. So that's a kind of abstract definition, but the way to think about it is to say, choose some indecomposable summand of T, count how many times it appears in T0, minus the times it appears in T1, and that's the coefficient in front of it. You should think of it as a vector of integers in this basis. And indeed, if you're interested in cluster algebras, this is how you categorify G vectors for cluster variables and cluster monomials. But I said I wasn't going to talk about that, so let's not. Let's recall the definition of the index or the G vector. It's still up there on the screen. Another result, this one is due to Palu, is that the G vector is not additive on triangles, but it's additive on certain kinds of triangles. What do I mean by this? Suppose I have a triangle like this in my cluster category. I would very much like to say that the G vector is a function on the Grothendieck group. In other words, I'd like to say that the G vector of the term in the middle is the sum of the two G vectors of the two terms here. This is not true in general, but we control how much it isn't true. And it is true if this last morphism here factors through add shift of T. So G vector is not a function on the Grothendieck group of the cluster category with the triangulated structure, but with respect to a certain nice class of triangles, it is additive. Now, if you come from the cluster algebra world, maybe you know that there's, depending on your conventions, positive and negative mutation, depending on the sign of the C vector, the mutation you're doing. And these kinds of triangle arise whenever you do a positive mutation inside your cluster category. So these aren't kind of natural triangles to look at. So we will, instead of thinking of the whole triangulated structure of the cluster category, we will restrict to the class of such triangles. So let's give a name to this class. So this curly E index T, this really depends on T, will be the collection of all triangles satisfying the property that the last map factors add sigma of T. Now, this collection does not confer a structure of triangulated category to C, but if you define the following bimodule, this is a bifunctor really. This is a sub-bifunctor of the X1 functor in the cluster category. You restrict to all those morphisms H that factor through add sigma of T. If you define this bimodule, then using work of Herschen, Liu, and Nakaoka, you can see that the cluster category with this bifunctor, or if you want with this subclass of triangles, becomes an X triangulated category. So that's a more general structure than a structure of triangulated category. If you're not familiar with extriangulated categories, I really encourage you to go and look at Y.Palu's lectures from last week's workshop. Okay, so we started with a triangulated category. It has a collection of triangles that comes with the definition. We restricted ourselves to a sub-collection. The new category, well, the same category with this new collection is now extriangulated. Why is this a good thing for us? Well, I'll tell you in a second, but before that, I want to tell you about some properties of this extriangulated category. First, well, zero property really. It's still home finite and it's still Kohl-Schmidt because I haven't changed the category. But now it's extriangulated because I have changed the collection of triangles. First, real new property, T is projective. That's not true in the cluster category. There are no projective objects. Its shift is injective. That's again not true in the cluster category with triangulated structure, but it is for this extriangulated structure. Second property, which is a bit of a strange one. If you take any projective object, then the morphism from this projective to zero is an inflation. So it's the start of a conflation for the extriangulated structure. And the way to see it is to complete this inflation into a triangle in the cluster category. And indeed, this works. Yeah, if you were to complete this into a triangle, you would have the identity from sigma r to sigma r here. This factors through sigma t, but it's fine. So this is a conflation. This is a bit strange if you're used to module category. Normally, there's no short exact sequence with a zero in the middle, except for the 0, 1. Another nice property is that this extriangulated category is hereditary. So any object has a projective resolution of length 1, or if you prefer, any x lies in such a conflation where the two first terms are projective. So global dimension is 1 for this extriangulated structure. And finally, and without going into too much detail, this extriangulated category has Auslander-Reten-Serre duality in the sense of the Yamanaka and Palu. The upshot of this is that you have almost split conflations. And you have one that starts in any non-injective indecomposable and one that ends in any non-projective indecomposable object. Okay, so this sounds like a nice structure, except maybe for this second property, which is a bit strange. Okay, so I'm only, well, in this talk at least, I'm only concerned with the cluster category with this relative extriangulated structure, but everything I will say from this point on would work for an extriangulated category satisfying these points. And so I keep these 4 points, these 5 points here. And a different example of this would be if you take any Artin algebra lambda and you look at two-term complexes of finitely generated projectives over lambda, this category satisfies points 0 to 4. So everything I say from now on is also true in this category. Good. Another thing that's useful to know is that, well, you know this already if you use the cluster category. The cluster category has as many indecomposable objects of a certain module category plus shifted projectives. How do you make sense of this? The home functor from T to anything induces an equivalence of additive categories like this. This is due to Born-Marsh-Reten in the case of the cluster category, but it's still true with approximately the same proof for an extriangulated category satisfying these 5 axioms. So we've generalized the setting that we're used to if we're categorifying cluster algebras. Okay. Now we come to the main part. How does this help us categorify G vectors? This helps us when we look at Grothendieck group. So I've put the setting again. C is a triangulated 2 Calabi-Yau category with cluster tilting object. Think generalized cluster category. And I have a relative extriangulated structure in there by taking a sub-collection of triangles. Okay. Now, first construction is that of the split Grothendieck group. The split Grothendieck group is a free abelian group generated by symbols corresponding to isoclasses of indecomposable objects. Another way to phrase this is to build, that's the way I've written it here, you build a free abelian group generated by symbols corresponding to just objects, and then you quotient out by relation corresponding to taking direct sums. So this gives you a free abelian group, generally of infinite rank. So that's one extreme of this picture. At the other extreme, you can remember that C has a triangulated structure. So there's a Grothendieck group for its triangulated structure. What does that mean? Oops. It means that you do the same construction. You take a free abelian group generated by symbols corresponding to objects, and now you quotient out by relations corresponding to triangles. Okay, this you can do for any triangulated structure. And now we have a structure in the middle. We have an X-triangulated structure. So you can define the Grothendieck group for this X-triangulated structure. And it sits in the middle, yes, because we only quotient out by a subset of relations for the Grothendieck group of the triangulated structure, yes. We only consider some triangles. So it sits in the middle. The good thing about this Grothendieck group in the middle for the X-triangulated structure is that it's free of rank n. It's free generated by the symbols corresponding to the indecomposable objects, indecomposable summands of T. If there's one thing that I like about this work is that this new object is where G vectors live. And why is it new? It's because, well, we already had this Grothendieck group of the triangulated category here, and it's still generated by the indecomposable summands of T, but sometimes it's very bad. Sometimes it's 0, even in type A2. Yes. So you cannot see G vectors in there. There are too many relations. So we forget it. We just keep this new X-triangulated structure and look at the Grothendieck group. And I want to expand a bit on what I was saying. So this Grothendieck group is free abelian generated by the indecomposable summands of T. In other words, it's isomorphic to the split Grothendieck group of at T, which is where the index lived. Yeah. And if you take an object in your category, its index is just the projection of X into this quotient, this new Grothendieck group. So from now on, the index or the G vector of an object is its class in the Grothendieck group for this X-triangulated category. This is how I want to think about them from now on. So this, for maybe trivial reasons, makes me extremely happy. Yes, G vectors live somewhere, and but can we obtain some new information with this? So this is what I would like to talk about now. So I've kept this projection. Yes, you take the split Grothendieck group of your category, you take an object and you send it to its G vector, living in the Grothendieck group for the X-triangulated structure. I call this projection G because X is sent to its G vector. Yes. And now I'm going to ask a question which may not sound natural, but which was motivated by something I'll talk about later. What is the kernel? In other words, what are the relations in the Grothendieck group of the cluster category for its X-triangulated structure? If you think in terms of cluster algebras, you know that positive mutations are additive with respect to G vector, and negative mutations not so. And a question you could ask is, what is the minimal set of relations between G vectors that I need in order to get all of them? Now, by definition, this kernel, this is just the definition of the Grothendieck group for the X-triangulated structure. Yeah, whenever I have a conflation, I have a relation. That's a lot. Can we do better? this is where we start looking at certain special conflations, the almost split conflations or Auslander-Reten conflations. Yes. For any indecomposable not injective, there's an Auslander-Reten conflation starting in this object. That's a conflation, so it gives us a relation in the Grothendieck group. I'll call it L of X. L is for left, yes, because X is on the left here. You could define R of X dually and obtain results written dually as well. Notations now. And the first result is that obtained with Arnaud, Jan, and Vincent, is that your cluster category has finitely many indecomposable objects up to isomorphism if and only if the Auslander-Reten sequences generate the relations of the Grothendieck group. This, I've said in a different way what's written on the board. So. It's an if and only if, so it's a way to detect categories that only have finitely many indecomposable objects. In that case, you can say more. The set of Auslander-Reten sequences is a basis of the set of relations, the kernel of G. That's a free abelian group. So I mean a basis as a free abelian group. And you have a formula given an object in this kernel, an element in the kernel. We have a formula to express it in terms of this basis. Formula itself is not so important, but I wanted to write it because a consequence of it is that assuming you're in the finite type situation, if you have a conflation, so this generates a relation, this one is, of course, a linear combinations of the Auslander-Reten sequences. They form a basis, but it's a positive, well, sorry, non-negative one. I'll draw an example later. So any conflation is a non-negative linear combination of Auslander-Reten sequences. Now, this may remind you of some previously known results. That's a remark I want to make. So the formula above, the one I've put in the equivalence above, yes. So there's finitely many indecomposable objects if and only if the Auslander-Reten sequences conflations generate the kernel of G. This is analogous to a result proved by Butler and then Auslander in the 1980s for the module categories. An algebra is representation finite if and only if the relation of it in its Grothendieck group are generated by the almost split sequences. Exactly the same statement, but our statement is not a generalization. Yes, our extriangulated categories are always hereditary, and there's always this weird sequence from a projective to zero to an injective. Yes, in our Grothendieck group, projectives and injectives are opposite to each other. This never happens in a module category. So our statement is analogous, but it's not a generalization of this result of Butler and Auslander. Now, recently there have been other similar results. Well, analogous results, one by Enomoto for exact categories with enough projectives, and another one by Haugland for triangulated categories with a cogenerator. I'm missing some hypothesis in both cases, just for shortness. Okay, so that's the first remark. Second remark, the reason we were looking at those is we were inspired by work of physicists Akani Hamed, Bahe, and Jan, who were looking at these relations. Well, I'm reformulating, but they were looking at objects that depended on relations in the Grothendieck group in type AN. And these results were generalized by mathematicians, Savan, Thomas, and Yildirim, for any acyclic Dynkin type. Well, Dynkin type with an acyclic initial C. So what we did was generalize these results for any cluster category of finite type. And we could obtain some applications to cluster algebras. But I told you I'm not going to tell you about that, so I won't. Another remark is that this formula here, yes, if I have an object in the kernel of G, I can express it as a linear combination of the Auslender-Rayton conflations using this formula still makes sense if you have infinitely many indecomposable objects. This sum is going to be finitely supported. The formula itself still makes sense. I don't know how to make sense of it though. But I thought it worthwhile to point out that this equality can still hold, even though it's an infinite sum. Okay. Maybe we look at a small example just to see what happens. So type A3, that's almost the smallest I could draw. Here's the cluster category in type A3. So the arrows in purple, well, the dots are indecomposable objects. The arrows go from left to right. And the ones, everything in purple is a fundamental domain because the cluster category repeats itself. Yes, it's periodic. So this object here and this one here are the same. Okay. And every triangle like this, or every square like this, is an almost split triangle in the cluster category for its triangulated structure. Now, if I want to look at the extriangulated structures I was looking at, I need to choose a cluster tilting object. So let's choose one. I chose one so that its quiver width relation was cyclic, yes. And now I can wonder, what are the Auslender-Rayton sequences for this choice of cluster tilting object? And I've drawn them in red here. So every conflation here, this square, this triangle, these are Auslender-Rayton conflations for the relative extriangulated structure in my category. How did I find them? It's all Auslender-Rayton triangles that don't end in one of the TIs. And the claim is that if you choose any triangle in there, any positive triangle in there, you can express it as a non-negative linear combination of the ones in red. Okay, so that's for the example. In cluster algebra terms, without spending too much time on it, these red conflations gives you relations between the G vectors, and these actually generate, they form a basis of all the relations between G vectors of cluster variables. Again, since I didn't assume that my field was algebraically closed, this works for any type A, B, C, D, E, F, G in cluster algebras. Okay, so some final remarks. First, sometimes, like in the cluster category, the Auslender-Rayton conflations are mutation conflations. So that gives us information on the G vector family. I'm not going to tell you how, but it does. Sometimes Auslender-Rayton conflations are not mutation conflations. This is an example. So if you take the pre-projective algebra in type A2, Auslender-Rayton conflations are not mutation conflations. So it doesn't give you information on the G vector family. Another comment, sorry, I should have stated this as a problem. We don't know how to do this. Yes. We would like to find a basis of the kernel of G when there are infinitely many indecomposable objects. And in small examples, it seems that it might be possible, but that we lose positivity, that we lose the fact that any relation can be written as a non-negative linear combination with those. And finally, we're thinking there may be possible applications to the U equations of Afghani, Hamed, Bayre, and Yan. But that's work very much in progress and conjectural. I'd like to end here. Thank you very much.
Very much, Pierre-Guy. Are there any questions?
Yeah. So if I get it right, every choice of T gives you an extra triangulated structure on your C, on your
Yes,
category.
that's correct.
And if you, for a fixed T, take the anamorphism ring of that,
Yes.
and look at the two-term category which you mentioned,
Yes.
will that have the same extriangulated structure as?
No, because it's not the same category. But there's a result of Brüssler and Yang telling you that if you take the cluster category and you quotientile by all morphisms going from sigma T to T, you get this two-term category of complexes. Is that right?
So they are equivalent. So they are equivalent as extriangulated categories.
Do we have a proof of this? So we I should say who is we. So Xinfang, Matt, Presland, Y.Palu, Mike Gorski, and myself are looking at things like this, and I'm not sure what the status of this is, at least conjecturally, and I'm pretty sure this is true. They have the same extriangulated structure, and maybe we have proved this, but I can't remember now.
It's a fair statement.
Is it the first statement with proof?
No, I think.
Okay, that's right.
But is the two-Pilaud structure essential for that in any way?
I don't see how, but it makes me nervous.
Yeah.
So the two-Pilaud structure is important for the rest. So was that what you say?
No, not for the statement on Grothendieck groups. This works for any extriangulated structure with projectives and injectives and the properties I mentioned before. But most of the examples I have in mind are I want to have applications to them, and then I think I mostly use the Pilaud property.
Yeah, we use it in a subtle way, so I'm a little bit unconfident about saying we don't use it.
Yeah,
We might do.
does make me nervous. Yeah.
Could you go back to this picture with the red shading? So then if you combine this with this Björn-Marschreiten result, then every indecomposable gives you one of these LWs, is that right? Over the endomorphism? I mean, you take away the T's, right?
What I mean is that the T's are not taken away. They're still in the Grothendieck group. I don't kill them.
No, just look at the conflation.
Yes.
You get one for every indecomposable module over the endomorphism.
Yes.
Is that
Yes,
always
that's
like
correct.
that, or is this finite type?
In this context, there will always be one almost split conflation for every indecomposable that is not injective. So there's one Lx for any Lx that's not injective, and the injectives are the shifted projectives. So by kind of numerology, the answer to your question is yes.
Okay.
So maybe it's a bit out of place, but you know, as there are triangulated categories and n-triangulated categories, x-triangulated and n-extriangulated are then n she vectors and n
So
and
yes.
n results on that.
So yes, I remember reading a paper of Peter Jorgensen and maybe someone else.
Or maybe
On
that's
this
what he wants to say, because
work
I'm
of-
looking at the chat right now, but I don't see what he's saying.
The paper's by Amit Shah and me.
Thank you very much, Peter. It's because you came give a talk on it. Yes, so I remember that.
In fact, I had a comment along the same lines. Pierre-Guy, you mentioned previous results by Butler, Auslander,
Yes.
and Morto and Haugland. My comment is that you could add Francesca Fedele to the list. She's got previous results precisely in the N case.
Yes, that is correct. Thank you very much. Apologies for omitting this. Well, forgetting. I did not omit it.
Yeah, I have a question. Pierre, thank you for the talk. I would like for you to explain a bit how you have some information in the G vector fund using these results.
Yes, is this Ippolito?
Yes. Okay.
So the very quickly, maybe I can show you some of my bad left-handed handwriting. So very quickly, if you have, say, this is the G vector fan in type A2, and we're interested in viewing it as a normal fan to the generalized associahedron. So here's, this should all be right angles, yeah. But there are several ways to do this. There's infinitely many ways to do this. The relations, positive relations in your cluster algebra, between G vectors in your cluster algebra, give you relations in your fan. Like you have a cone here, and you have an adjacent cone here, and you have three rays in a dimension 2 space, so there's a relation between them, and this relation is given by a positive mutation relation in the cluster algebra. So this is where the link is with the Grothendieck group. Sorry, that was really quick.
No, thank you.
We have a question from Greg Musica, who says, does the number of AR conflations depend on the choice of T?
No.
And in particular, are these the relations between all G vectors, or only between the G vectors reached from the original quiver by the positive mutation?
Between, if you mean by all G vectors, if you mean all G vectors of cluster variables, then yes. You do get all of these relations.
But if you're in the Markov case or something like that, you're not saying anything about it. And they're not that different, I suppose. The other
so if you're in the Markov, then you're not in the situation where you have finitely many indecomposables, so it gets harder to say it.
Okay, one more question.
Henry's my objection. So you had two maps between three groups, right? You've only told us the kernel of one, which is the kernel between the split and your one that you're sort of introduced. But the kernel of the other map is, I think, generated by the higher Icelanderite sequences of the Y.Palu. because I think that's encoding the difference between the what relations do you need between your cluster tilting object to generate the actual K-theory, I think is exactly what the hierarchy is doing. I was just wondering, what is the philosophy of why this G is better? Because the G is somehow between the split thing, which is this sort of massive, sort of crazy object, and the thing that's generating the well, the cluster tilting object. Is the philosophy, is the K-theory, is this kernel somehow encoding how, what's the philosophy?
I don't know that I have an answer that will completely satisfy you, but maybe one thing I like about this is that we knew, like, without thinking numerically, you know that an object in the cluster category is presented by these objects in AdT, and you know that it's if X is rigid, then this object is more or less determined by what are these two objects in the presentation. And this gives you a numerical thing called the G vector, which lives nowhere if you don't have this extriangulated structure. So for me, philosophically, in some sense, I was happy that this numerical invariant lives somewhere, actually. It's the class of the object in a certain Grothendieck group.
Can I add a comment, maybe? I mean, I think you said it already, but this Grothendieck group at the bottom is often zero. I mean, in half the type A cases, it's zero. So if you take the image of an object there, you get no information.
Yeah, but that's just telling you your hierarchy is generating the zero group, right? That's fine. That's the language, right?
Yeah, but if you want to learn something about your object, I mean, you get more information out of this. Maybe I'm not sure I understand your question. I mean, you can distinguish rigid objects, for example, by the G vectors in this set. Whereas...
Yeah, but that's you're making a statement of the middle group. But what I'm making a statement of the top map. Why is that natural?
So maybe I'm not sure for sure. We had the split Grothendieck group, and then there was the extriangulated Grothendieck group, and then there's the triangulated one. There's everywhere. So the top map is the G one, is the one I like. So it's And well, yeah, philosophically, I like it because it means G vectors live somewhere. They're not just some numerical coincidence.
I could maybe add something to this from my recent paper with Amit. You've got other intermediate quotients which actually sit between the top and the middle object, where you mod out even fewer relations. These can also be realized using extriangulated categories. It's nice to do so because these intermediate quotients had appeared in previous papers on phrases as completely ad hoc objects. Nobody knew where they came from, but they can be realized along precisely the same lines. You just use other extriangulated structures.
Have a question? Okay, thank you very much. There's clearly scope for many more objects in between these two. So we'll leave that to further discussion. So we shall continue in 5 minutes. Okay, Thomas Brewster's story. And let's try.